is
That's quite Good afternoon. We're going to begin 15 minutes early because we have a lot of excitement ahead, and I don't want to limit the amount of time that we have to talk. Thank you. This is a panel discussion on cloud networking and SDN. Deep has asked me to give a few opening remarks about the IEEE Cloud Computing Initiative and Intercloud and how we got to this place. And I'll do that before we start the panel and I introduce the panelists, and after which we'll have a Q&A. So I hope this will be an interesting, interactive, exciting afternoon. I'm very glad to be here today at IEEE CloudNet and to see the development of the conference in its second year, and I'm looking forward to seeing it grow as the years go ahead. The reason I'm here today is because of the IEEE Cloud Computing Initiative, which is a sponsor of this conference. And I wanted to begin by telling you how we got started with cloud computing in the IEEE and how you can participate and help move the process along. Some of us may be old enough to have been around when the internet started, but a few years ago, a number of us, and some of us you've heard speak already, at Cisco Systems 5 or 6 years ago, started thinking about the cloud computing wave as a repeat of the internet wave, and we began to wonder what we could do to move the process along more quickly based on what we learned from the previous waves of computing. I started showing a slide back then that showed 4 waves of computing with mainframes, PC and client server, the old Sun Microsystem workstation world, web, and cloud. And this slide worked for a few years until a number of us started realizing that cloud computing was not an end in itself. It was a way to re-engineer computing to impact data centers, but it wasn't the ultimate destination that we were traveling. And what really was happening was the confluence of social, mobile, IoT, and big data enabled by cloud were not just changing computing, but were changing all of our lives. And so the slide that I started showing after that was this slide, where I added those elements to the slide for cloud computing and started seeing this as a larger process. One of the things that we learned in looking at cloud computing and the history of the development of the internet was a way to look at this model that looked at users, software, and resources. And I came across a model that IDC developed in 2012 called the third platform. And basically, they started out with the first platform being mainframes, mini computers, and terminals, and there were, in that world, millions of users and thousands of apps. I worked in computing in that world. How many of you in this room go back to the first platform? Not many hands. Oh, good, I feel better. Some people I know go back to that platform and didn't raise their hand, Masum. It could be a hearing problem. The second platform was the LAN, Internet, PC, client-server platform, where we had tens of thousands of applications and hundreds of millions of users. And that platform has been extant for quite some time and has created a huge marketplace, tremendous change in our lives and in computing. But the big change that IDC is talking about is the third platform. And that's where we have millions of apps, not thousands or tens of thousands, but millions of apps, billions of users, but more importantly, in the Internet of Things, hundreds of billions of things. Incidentally, in that model, we're creating exabytes of data a day with all those things. So the question is, how do you really make this happen? This is the vision, but it doesn't talk about how to enable it and how to make it happen, and that's part of the reason why we're all here, is to figure out how to make this work. What are the bottlenecks? And one of the things that we saw as a bottleneck was the development of the cloud and how to make that happen based on what we learned from the internet. So this is a slide which is similar to the one that David Bernstein probably used in his talk, but I replaced the telegraphy with the first commercial telephone exchange, which was in 1878. And for you telephone users out there, there may not be very many anymore, this telephone exchange was capable of handling 2 simultaneous conversations. So you should be really impressed, because 2 sets of people could carry on conversations through that telephone exchange. It took 83 years to get to the point where you could pick up a telephone and dial a number anywhere in the world. We call that federation. Up until that point, you had to call an operator, and that operator had to call another operator, and maybe another operator, and pass the call along. That's the situation that we want to avoid in the development of cloud computing, because that retards the development. It retards the kind of applications that you can compose and makes things much more difficult. However, this is the same situation that those of us who worked with email in the 1980s faced. Let me ask that question. How many people had an email account in 1980? Oh my goodness. Okay, was that 3 or 4? All right, 5. Okay, good. Well, in the early days of email, there were islands of email. And so an email address was not just s.diamond@computer.org. You had to know what email system they were on. And if you weren't on the same email system as the person who wanted email, you couldn't send them an email. Maybe you could email someone else and ask them to print it out and carry it over to their office, or maybe phone them. Obviously, not a good system, not really an internet. So what did we have? We had a bunch of standards that caused the carriers to federate. We had TCP/IP, we had DNS, we had SMTP in mind, and we had a bunch of IETF standards. And suddenly we had an internet where you could send an email from one person to the next. And that's really when the internet exploded. We're in the same situation today with cloud computing. We have a bunch of carriers or cloud computing service providers, but they don't all federate. And the question is how to make that happen. Well, we've invented a few names of protocols that are needed, and I'll talk about some specific work that's going on, but basically we need the same kind of thing that happened to enable the internet to be the extremely powerful engine that it's become. We need that to happen for cloud computing to reach its potential and to enable the third platform that's going to enable hundreds of billions of things and billions of users. The typical approach to cloud computing is what I call the multi-cloud approach. You have several cloud service providers, they have APIs, the users have to program to those APIs. And if you want to write an application that involves more than one cloud service provider, you need to use more than one cloud service provider API. Now those APIs are not standards in the formal sense, and they have the potential for changing, which means you have to change your interfaces as a user. You might also have a cloud broker who takes some of this complexity and makes it invisible to you because they deal with the multiplicity of service provider APIs. One of our colleagues that we work closely with in the IEEE, Raj Kumar Bhuya, who's the incoming EIC of the new transactions on cloud computing, he's involved with a company that does this, and I've had conversations with him. It's extremely difficult. It reminds me of the old days of the internet when there weren't APIs, and if you wanted to interface with someone's website, you had to do screen scraping. Well, it's not quite that bad, but keeping track of multiple APIs is not something you really want to do. The solution is the Intercloud approach, where there's a standard API that multiple cloud providers offer. They may also have proprietary APIs. And the users can write an application to compose resources across the whole cloud. One API that gives you access to the whole cloud, and that should be a standard. And it should be controlled like standards are, like 802.11n or some other revision of a standard. And that's the idea. To make this happen, there are also other assets that are needed. An intercloud route, which is something like DNS, an intercloud gateway, which mediates data, and an intercloud exchange, which mediates governance. This is a project that's underway, in particular at IEEE. IEEE P2302 is a project to build an intercloud API. There's lots of other standards work going on in the world, but P2302 is particularly focused on this kind of standardization, and we'd love to have your involvement in this work. This is a slide I think David showed you earlier in the week, but this is the vision for the kind of intercloud that we could create using P2302, and the entire IEEE is involved in making this happen. The IEEE Cloud Computing Initiative is an initiative that was funded by the IEEE Board of Directors. We're in our second year. Next year will be our third year. I chair the initiative, and we have 7 tracks: publications, conferences, education standards, big data, testbed, and a web portal, designed to bring together the whole IEEE in a way that will accelerate the development of cloud computing, in particular intercloud, and reach this vision that we've been talking about faster and in a way that's more effective. If you're interested in participating in any of these elements, of course you're here at a conference, and we're glad to have you here at a Cloud Computing Initiative sponsored conference. We'd love to have you participate in the Cloud Computing Initiative. We have a web portal, cloudcomputing.ieee.org, which pulls together all the activities across the IEEE that the Cloud Computing Initiative is sponsoring. You can find pointers to all of these things there, all of the conferences that we're involved in, the standards, the publications, and so forth. Keep your eye out for transactions on cloud computing, which Raj Bhuya is EIC of, as I mentioned. That's coming soon. Shortly thereafter, we'll be launching Cloud Computing Magazine, and next year, transactions on big data. So there's a lot going on in the IEEE initiative. The vision is to accelerate the development of cloud computing so that this vision of the future cloud that I think we share can be brought about sooner, and that the lessons that we learned in the development of the internet can be applied based on the values of the IEEE. So that's my introduction. I'll be here after the panel, and I'd be glad to talk with any of you who are interested in learning about how they might participate in this. And of course, by being here at the conference, you're already contributing, but we'd love to have more of your interest and time and understand what we can do to help move cloud computing along from your perspective. All right, so next I'd like to introduce our panelists, and we're going to talk about cloud networking and SDN. And the format is that each of our panelists will make some initial remarks, and then we'll have the floor open for your Q&A. So while the panelists are talking, please think about your questions, and we'll have enough time afterwards to answer your questions. Jennifer Lin is the Senior Director for Product Management at Juniper Networks. Before that, she was the founder and VP of Marketing at Contrail Systems. Amol Mahajani is the VP of Engineering for SDN at HP Networking, and prior to that, he was the VP of Engineering at Infinita Systems. And Masum Hasan is a Technical Director at Cisco Systems, my old company. Prior to that, he was a Principal Investigator at Bell Labs. Please join me in welcoming our panel, and then I'll turn the clicker over to Jennifer to begin.
Okay, I guess I don't need the clicker because I am the only panelist up here that doesn't have slides. But I will point you to a plethora of information about what we're doing at Contrail right after this. We recently did a launch and we open sourced our technology, and we're getting an incredible amount of validation and feedback. So I'd like to share that with you. Yes, I lead the product management effort for our Contrail Systems solution. We joined Juniper in December with the acquisition of a small software startup called Contrail, which, for those of you that don't know what a Contrail is, it's essentially a man-made cloud. We were almost 50 people, almost exclusively software engineers at the time that we were acquired. And we took our Series A investment from Vinod Khosla, which, as many of you folks know, in Silicon Valley is considered sort of one of the fathers of he was a co-founder of Sun Microsystem and started a lot of the early discussions around trends around cloud computing. Efforts around virtualization for us, there's been a lot of discussion around network virtualization recently, but I think for those, since all of us spent 12 years at Cisco prior to Juniper and prior to Contrail, companies like Cisco don't consider network virtualization a new concept. In the server virtualization world, when you have people talking about network virtualization, it kind of comes across as a brand new thing. But in cloud, we consider virtualization really a key ingredient that actually many of the concepts are actually quite mature. So the goal that we had as Contrail was really to look at the trends that cloud was introducing and the key inflections for networking that were really leaving a lot of gaps in our customer base. Given the fact that many of us had spent, more than a couple of decades in the networking space, I've done a lot in wireless and mobility and drove a lot of the early machine-to-machine efforts at Cisco around smart grid and IoT. A lot of that was around now with this hyper-connectivity and the fact that there's this explosion of data because the number of endpoints is exploding, and because essentially each of those endpoints is not only hyper-connected at all times, but essentially instrumented to produce a lot more data. There's a lot more analytics around all this machine-generated data. And as that rolls up to support new types of application archetypes, namely for Contrail, we were looking specifically at 3-tier web applications as well as big data analytics. They're really putting new pressures on the network. What that's causing, as I think many of the folks earlier talked about, is a move away from traditional, especially in the data center, 3-tier switching architectures where you have access, aggregation, and core switching hierarchy, and more like what the Googles and the Facebooks and the Amazons are doing, which is really running their data centers as a flat IP fabric, almost as an extension of the internet. What we were doing at Contrail, and employee number one at Contrail is someone named Pedro Marx, who was a distinguished engineer at Cisco and then moved to Juniper, distinguished engineer there. In his career, he was driving a lot of the IET efforts around L3 VPNs and drafted a standard almost 2 years ago now with AT&T and Verizon and others in the standard space around the notion of L3 VPN end systems. And really the problem that they were trying to solve is in these cloud data center environments, how could we solve some of the problems around a scale-out horizontal scaling architecture which was very elastic, so that as you had cloud users who expected to self-provision compute and storage resources, the network was essentially automated to just come with it. That's the problem that we were solving in a lot of our carrier and enterprise and emerging web company customers. That's the problem that they're seeing in the gap in the industry, that there aren't a lot of baked solutions around. But to kind of echo what Steve was saying before, if you think about these trends in terms of where computing has evolved and where networking has evolved, one of the key things, SDN started and was incubated in Stanford, and another one of our founding team members spent those early days in the Stanford Computer Science Department, where the problem that SDN was trying to solve was, how do I take production level network traffic flows and redirect them, in this case to the Computer Science Department, so we could do some interesting research on them and manipulate those flows. That campus slicing example was one of the beachhead use cases for SDN and where a lot of the early OpenFlow work was done. But many of those building sort of large scale-out data centers looked at that and said, well, that's a very academic exercise. It doesn't really address my operational concerns. It may not address my scaling concerns. How do I essentially do things like in-service software upgrades when I have a single failure domain and a highly centralized control point that essentially could take down my entire network in one fell swoop? So in this evolution of, we didn't use the term SDN as contrail, but in this evolution of the dialogue around cloud networking, and I think, like what we're doing here in efforts like this, is really to back up and say, if the notion of cloud is going to become real, where essentially you have these federated elastic architectures and locality doesn't matter. I have the freedom to move workloads where I want to. Virtual machines can move. I can have this scenario of cloud bursting where I might have a virtual private cloud in my environment and use resources in Amazon Web Services or Google Compute Engine or Microsoft Azure to essentially pick up those loads. Then the network completely needs to be abstracted. And the data models to allow that movement to happen need to be pretty well baked. I think a couple of us were in Hong Kong last week at the OpenStack Summit, and you can imagine that a lot of the discussion in venues like OpenStack is more around the framework and the schemas and the data models that are vendor agnostic to allow this federation to happen. The L3 VPN end systems work basically took a couple of assumptions. Number one, the technology on which Contrail was based came from that IETF work, but essentially we do use and reuse BGP for federation, because a lot of the mindset by our large-scale carrier customers was, let's not reinvent the wheel, let's use mature protocols that are pervasive where they're applicable, and let's solve the new problem. Now the new problem is that you now have servers and virtualized server environments where you may have up to 100 virtual machines per server. So we've introduced this notion of a vRouter that sits on the hypervisor or on the Linux kernel and essentially distributes some of that routing load right down to the host. And by essentially distributing the edge of the IP network down to the hypervisor, obviously we can do a lot of policy enforcement, we can distribute a lot of the services, and we can have an architecture that extends essentially mature layer 3 paradigms within a virtualized data center environment. If you think about a lot of the web scale players, whether it's Amazon or Microsoft Azure or Google, Facebook, they've been running protocols like BGP in the data center because they had to. And many of the vendor solutions did not have that paradigm because they were using essentially VLAN-centric approaches. But they needed, because of the workloads that they were driving, much more flat any-to-any connectivity to much more distributed workloads. If you think about Amazon and the web page that they're serving up to you, it's highly personalized to who you are, where you are, what you bought, and the distribution channels that will serve you and deliver that goods to you in the next couple of days. So there's a lot of data crunching that goes on. And you probably have often heard that within a data center, whereas the client-server loads used to be 80% north-south, now 80% of that load is east-west. So we're breaking through that sort of layer 3 boundary a lot more, which is causing sort of the limitations of, exposing the limitations of sort of VLAN-centric architectures. As a product, our Contrail solution, we GA'd or made generally available our product in the last few months. We have been working with a combination of global carriers as well as enterprise and emerging customers like gaming customers who are building large clouds for massively multiplayer games where there's obviously a lot of real-time processing and the workloads are highly mobile. And what many of these customers want to be able to do is have full flexibility. They may, for instance, be a startup, like Contrail. We did a lot of our early development in a cloud environment because we didn't want to build a data center for our workloads. But as we grew, essentially, we moved that into a colo hosted space. The types of things that we're looking at from a network perspective is how can we take essentially the AWS VPC model, virtual private cloud model. So Amazon, as they started to evolve their AWS service, they started to provide a VPC service to the enterprises who wanted to be able to carve out a private address space for their own workloads. If they want to then repatriate those workloads into their own private data center environments, there's a lot of overhead in sort of re-scripting the environment and retooling the orchestration systems and all the back end to accommodate that load now in their own private data center. So the types of things that we've contributed into OpenStack are essentially the blueprints for how do we take those AWS VPC APIs and make them applicable in the virtual private cloud environment, let's say in a large financials data center. Many of our enterprise customers are using OpenStack, essentially moving forward to create private clouds for their emerging workloads. And I point out emerging workloads because they've already virtualized their data center environment for their legacy workloads, and they've spent the last 3 or 4 years essentially saving cost and consolidating data centers with server virtualization. But the new problem that they're trying to solve and where their MBOs are shifting, they're actually being incented and bonused not around cost cutting anymore, but more around how quickly can they roll out a new revenue generating service and how quickly can they differentiate, let's say, their mobile banking service so that they can competitively differentiate their core business. And for the IT organizations, they are in a period of either lose those workloads to public cloud or managed providers, or show that they can keep up with the pace at which these open source technologies are evolving. And so for the IT organization more broadly, we hear all the time that the CIOs are now forming tiger teams to converge the network, server, storage, and applications teams, for which many of the components of that new converged IT infrastructure are based on open source technologies. Since we've open sourced the Contrail software, we've obviously had a lot of global, Ukraine and Russia and China and a lot of our sort of prospective customers now coming back to us and saying, well, I've got, let's say, energy management in the data center. I want to be able to use your northbound REST APIs to have better feedback from what's going on in terms of specific flows for virtual networks in the data center environment. So I think that's, at the end of the day, it's all about the applications and what the applications are trying to do and how can the infrastructure best support that. One of the key things that you'll hear, whether it's an OpenStack environment or, let's say, Open Daylight, where they were trying to sort of solve the problem around how do we expose consistent northbound APIs from the network so that we can programmatically control the network and eliminate a lot of the manual CLI configuration that essentially accounts for a majority of the OpEx in an IT organization. We saw this same transition, I think, with wireless and mobility as folks move to mobility controllers. But I think we see a similar trend, and a lot of what we're doing for, let's say, large-scale carriers is enabling, wireless access services in a service chain way so that we can have that flexibility and deliver sort of more flexible and agile services. I'll kind of stop there because I think I'm probably through my 8 minutes.
Thank you, Jennifer. Next, Amol. Yeah. That's forward.
Hi, good afternoon, everybody. So, what I thought I would do is, let me just.
We'll get there.
Okay. So what I thought I would do is talk about three problems, and some of the problems have been already discussed, but in a slightly different context by Steve and Jennifer so far. So the three problems that I want to talk about is the network ownership, then federation, and then finally routing, right? So as we go along, I'll explain more on what I mean. So all this is in context of the data center or cloud networking. So the first part is ownership of the network. Now, over the years, over the last few years, we've seen different approaches taken by different companies on where the network function should reside. And as you can see, there are four different approaches. The first one assumes that the network is what it is, and mostly software-based vendors have chosen to do an overlay solution which is completely ignorant of the underlying network, right? So this is a good approach. It can work seamlessly. The other approach that some vendors have is, along with the blade servers, they have a blade switch. And that kind of causes confusion because you have server administrators who are configuring the virtual machines and the networking part on the vSwitch. You have your traditional underlay network, and now you have this additional edge switch which is coming from yet another vendor. And that clearly is a problem because the blade switch is kind of squeezed in the middle. The third approach is where the networking vendors are trying to go all the way into the virtual world, and that creates kind of a problem because now who would administer the networking on the vSwitch? Would it be the virtualization or system admin, or would it be the networking admin? Finally, there is a fourth approach where actually the overlay and underlay can work together regardless of where the solution comes from. You could have two vendors providing overlay networking solution and underlay networking solution, which is your existing network, and some way to work together to provide a much better experience. And that brings us to the next topic of if you do have vendors where one vendor is providing your overlay solution, one is providing your underlay networking, which is your traditional physical network. How do they work together to best provide a complete end-to-end control and management solution? And there are three approaches. One approach is where the overlay controller is kind of the master and delegates the configuration or the control of the underlay to the respective controller, underlay controller. The second model is exactly reverse, where the underlay controller is in charge and delegates some of the control for the overlay to the other controller. The third one is more side to side. And as we work with different vendors, we have to figure out which is the best approach because each one has pros and cons. Clearly the last one is probably the most complex because there is no definite control boundary, and depending on how you can implement the solution, the lines get blurred, and one solution that works with one vendor may not work with another vendor. As I said, these are some problems to consider, and clearly at HP we have a certain views, but I just want to open this as a problem and different approaches that are being considered in the industry. Finally, wanted to talk about routing. Jennifer mentioned on how they've developed a virtual router that sits on each of the compute nodes. And we've been looking at the problem and trying to see again which is the best way. Whether the router, which is distributed router that resides on each compute node, should it do the entire routing, or should it restrict itself to only east-west traffic, while having the north-south traffic be delegated to a traditional gateway-like router. The advantage there is the intra-data center or intra-cloud routing doesn't need to know all the external routes and bring in the complexity. The second approach is you have a complete centralized forwarding approach and not have any routing on the compute nodes. Clearly, that becomes a bottleneck and a scalability issue and challenge. The third problem could be more of a mix and match, where you can have certain centralized functions like VPN, IPsec, firewall, and IPS, and whatever you do typically at the gateway, and delegate that part to a traditional function, whereas the compute node doing only the rest of the routing. So these are different approaches that are being considered by different vendors, and remains to be seen which of these approaches will eventually be popular and deployed. Each come with its own problems, whether it's federation or routing. This is clearly an evolving field, and like I said, what is needed is also a sense of cooperation, where two vendors compete as well as cooperate to provide the best experience to the vendor. So that's just a quick note on what kind of problems we are looking at HP.
Thank you all. Let's pass this down to Masum. And you want the PowerPoint first, Masum? Okay.
Okay. So is this slide mode? Okay. Thanks. I'm going to talk about, my presentation can be a little longer than Amol's, it's okay, because I have also a video, 4-minute video. So I'm going to talk about a specific concept called seamless virtual clouds. Clouds, see that I use plural term there, clouds. So, this concept falls in the category of intercloud, hybrid cloud, community cloud, So let me get into that. So you all know about private cloud, public cloud, hybrid cloud, I guess. NIST has defined hybrid cloud as a composition of multiple clouds, right? So then NIST also has defined a cloud deployment model called community cloud, right? So now the question is that, you have this notion of hybrid cloud, private cloud, public cloud, hybrid cloud, and community cloud. Question is that, can I basically, as a infrastructure, as a service admin, create, read, update, delete the virtual clouds out of existing hybrid or community clouds, or private and public cloud, right? So, so that's the question, and in order to answer that question, we came up with this idea of seamless virtual cloud. I also, call it kind of, cloud squared, like clouds of clouds, right? So it's basically instances of clouds that you can create, read, update, delete out of existing clouds. So, so that's the basic concept, right? And then, in order to CRUD basically create, CRUD that the seamless cloud, the virtual cloud, basically, I as an infrastructure, as an admin, should be able to actually select, deselect on demand, like on demand in any cloud, right? Any resources that are existing in the hybrid or community cloud, right? So I'll basically select a subset of clouds and then create an instance of virtual cloud, right? I should be also able to actually select, deselect the tenant or enterprise sites, on-premises sites or off-premises public cloud sites, right? I should be able to, or even network segments, should be able to do that also on demand and include them in the virtual cloud, right? The other thing I would like to do also is that I should be able to, on demand, control the reachability between the resources and the sites in that virtual cloud, right? Why, I would like to do that because there might be consideration for the performance considerations, security considerations, and of course the regulation considerations, right? So now here, now let's look at this from a quote-unquote consumer or user perspective, right? So I talked about the infrastructure as a service admin, which is a kind of user there, but also you have the kind of end human user or application, right? User. Application as applications as users, right? Or application controllers. So when you have distributed application, you typically have a controller. Think about like Hadoop MapReduce, right? So the Hadoop has for example, controller that controls the placement of tasks, control the placement of data using HDFS, and so on, right? So, so any distributed application has application controller. So then what happens in here, we consider the end human user, the applications or application controllers as the consumers of this virtual cloud, right? So, so basically the idea here is that the fact that from a consumer perspective, that the instances of the virtual clouds, they consist of multiple clouds. That means they have resources or sites from multiple clouds is hidden from the consumers, right? But it is not hidden from the IaaS admin because the IaaS admin actually has to craft this create reliabilities of the virtual cloud. So so basically what happens in here is that the consumers see this virtual cloud as one seamless cloud. Basically, it sees this cloud as if the cloud, the virtual cloud actually, or the instances of the virtual cloud, they reside in the consumer's space. Meaning that, let's say that if the consumer is an enterprise, then as if the virtual cloud reside in the consumer, the enterprise intranet, right? Or in the enterprise public cloud. Now, in order to support this concept, you have to do a lot of magic in the network. So I'm going to get into that. So here, whatever I just said, pictorially or graphically or diagrammatically. So here on the top you see two enterprises there. That on premises, enterprise has multiple sites there. So here, enterprise T1 has sites in CA, San Jose, San Diego, and so on, New York. Enterprise T2, and then enterprise T1 also has site in Texas, right? Down here you see public clouds, right? So here you see that there is a public cloud CSP1, Cloud Service Provider 1 has 2 data centers, and here CSP2 has 1 data center, right? So now, as you can see in the middle, there's a gray box in here. It is hiding something underneath. You can see a little bit, right? So now think about the tenant T1 IaaS admin. It should be able to actually create the seamless virtual cloud like this. So it will pick and choose the resources that are in here. So in here you can see there are some resources in here. These could be VMs. Like in our case, these are some clients. wrapped in a VM. These are some servers wrapped in VMs. So the IS admin basically may create this seamless virtual cloud like this. So I just remove the T2. So those are the resources that will not be included in the seamless virtual cloud. So the IS admin has decided to include these resources in the seamless virtual cloud. IS admin, they may also decide to actually include a specific sites. That could be either the on-premises site, so that's not going to be included, or else it may decide not to include some of the public cloud sites, right? So then, this is the seamless virtual cloud. This is basically an instance of a cloud that has been created out of multiple clouds, right? And also out of multiple enterprise sites. So then, I talked about the requirements like performance, security, and the regulation requirements there. So what the IS admin should be able to do actually basically decide or control, basically on demand, control the reachability between the resources in this virtual cloud, right? So that's what being shown in here. So as you can see here, it shows that this is what we call vertical reachability. That means these are the resources on the CA region that will be reachable to each other. Then the New York resources will be reachable to each other. Then the Texas resources will be reachable to each other, right? So the IS admin will be able to control that, on demand. Then it should be also able to control like the what I call horizontal reachability, meaning that let's say that you are doing some big data crunching, right? At the end of big data crunching, let's say that you're doing Hadoop MapReduce, and then at the reduce phase, you wanna that at the reduce phase you have to aggregate the data, right? So then what you do, you actually create reachability horizontally, right, to merge the data. Again, you do on demand. And when you don't need it, you just get rid of the reachability, right? All this is done on demand, right? So now, let's look at the networking, network aspect of this, right? We, this is, we are going to talk about cloud networking in here, right? So, let me remove the gray box there. Right? So as you can see, there's underneath this complex network end-to-end, right? So it can be, of course, much more complex than this. This is actually our lab network. Actually, our lab network is more complex than that. So as you can see that there are two service providers in here, cloud service provider. The assumption here is that same cloud service provider like AT&T or Verizon may also manage the operator, manage the network. MPLS network itself and offer, let's say, layer 3 MPLS VPN services, right? Similarly for the other, the service provider. And as you can see in here, that the two service providers may talk to each other using a multi-AS layer 3 MPLS VPN, something that Juniper also, referred to, right? The idea there is that, if we have the existing framework there, we don't have to reinvent the wheel, just make use of it, right? So now, but in our case, if we have to create this seamless cloud, seamless virtual cloud that will give the consumer of the IS admin basically an impression that this is one single virtual cloud that resides in the public, the private cloud or the enterprise intranet, then we have to do something in the network that will enable the consumer basically or the tenant to get that impression, right? So that's where the magic comes in. You have to do some magic in the network. So one of the things that we have to do is end-to-end isolation, right? So if you look at the network in here, you can see that you have different segments of network. So you see there's a server access network, which could be OpenStack neutron controlled. Then you see northbound DC, and here network. Then, of course, you have the metropolitan wide area layer 3 MPLS or MPLS VPN network, right? So you can also, as I said, you can have multi-AS or CSC L3 VPN network there. So repeat the same thing up here, right? So now, I talked about that, the vertical reachability or the horizontal reachability, right? So for that, we have to actually provide end-to-end isolation. Not only for that, but also for multi-tenant isolation, which is multi-seamless cloud, virtual cloud isolation, multi-tenant isolation, we have to provide all these things. So for that, I have to have a way actually to somehow stitch these different segments of the network in a, and create isolation, right? So, and also we have to do it in a way so that the complexity of the network is hidden both from the IaaS admin and the end user, the consumer, and the applications, right? So for that, what we have done is this. Basically, we have defined a cloud abstraction, right, which is actually a graph-based cloud abstraction. We call it cloud squared graph abstraction. That basically allows a tenant IaaS admin to create this instance of virtual cloud, seamless virtual cloud on demand in a very simple way. And that actually hides the complexity of the network and the infrastructure underneath basically hide the complexity underneath, right? So if you look at this graph, you'll see that any component of this graph actually can be created, update, delete by a tenant's IaaS admin on demand. Any node, any edge. Once that is done, you'll see magic happens in the network. I'll show you the demo for that. So we have defined this graph abstraction, and then we have defined a REST-based API that basically incorporates the abstraction in the API. All right. So we will be publishing that API hopefully, soon in the OpenStack maybe or the SDN forums. The other thing is that the whole graph can be also cracked using a concept called monitor event condition action, right? So basically, an IaaS admin or any programmer can write program using our API to actually basically create craft the seamless virtual cloud autonomically, right? So now, so here is the so I mean, if you look at this, consumers, the end human user, or the applications or application controller, they basically see only the upper, this part, and this part. IaaS admin definitely sees the whole thing, but then as I said, that IaaS admin does not see the network, right? So now, let me just quickly run a video just to show, the concept in action. We have developed this, it is in a prototype stage right now. So yeah, could you please run the, So basically what you see, whatever I said just now, in action, right? We use the SDN, basically Cisco's version of SDN, like 1PK underneath. We use OpenStack controller to control the server access segment. So is there any way of pausing in here? No. Anyway, so what is happening in here? Sorry? Yeah. Go ahead. So what is happening, as you can see, that the user has selected sites in here. As you can see, that was prompted with multiple sites. Has selected a specific one. Selected the public cloud sites there. As you can see, the user is selecting, IaaS admin is selecting one specific server there, but not the other ones. Here is selecting all the clients and so on, right? So this is just shows how an IIS admin basically can create the seamless cloud. Now here what is being shown is that the IIS admin basically is creating what we call isolation abstraction, which is basically control on demand, the reachability, right? So what it is doing, it is actually incorporating all the sites in the reachability control, meaning that once this is done, can you pause in here? Once this is done, the resources up there and resources down there will be reachable to each other, right? Now, as I said that this can be done on demand, or, here we are showing like, we have connected all the sites, but an IIS admin can pick and choose, right? The reachability control. Go ahead. So now this will be submitted to the controller, Seamless Cloud controller, which is a kind of SDN-based controller. As you can see that here, yeah, it's not that easy to see. Yeah. So as you can see that we are using actually underneath MPLS layer 3 VPN there to create. Can you stop there a little bit? Move a little bit back. Yeah, just stop here. No, just a little bit more. Okay, stop here. Yeah. So what happened is that the graph basically got translated into programming the infrastructure. In this particular case, what is happening is that it is programming the infrastructure actually using OpenStack controller, especially the Neutron controller, to actually create the server access segment of the network, the virtual network. And then when it goes to the metropolitan wide area network, it basically program the infrastructure using Cisco's version of SDN, which is called 1PK. In this particular case, our underlying network is MPLS layer 3 VPN, so it is programming the layer 3 VPN network on demand. In fact, we have defined an on-demand API. Hopefully, we'll be able to also publish that. In fact, we have an IATF draft on that. So basically invoking that API, on-demand API, to program the MPLS VPN network. So that is happening in here to create end-to-end isolation and to basically create the seamless virtual cloud, but at the network layer. Right? Yeah, go ahead. So next you will see that the OpenStack controller basically is bringing the Neutron network up, right, on demand. It is happening on demand. So as you can see also this green, you can see that is bringing on demand and then connecting into the MPLS network underneath. Now we cannot show, can you stop in here? So we cannot show the whole topology in here because the OpenStack graphical user interface does not support yet the the whole network. It supports only the access segment of the network. Hopefully, we'll incorporate that in Horizon maybe later. But this is what is happening in here. So in the graph, you see that you just connected some nodes and edges. A lot of things are happening underneath in the network. Very complex things are happening in the network that we are showing in here, right? Go ahead. Similarly, the other server is coming up in here. And you'll see that what we did actually, so those clients actually, they are connecting to video. Now, so here the California side, New York side, Texas side. So you'll see that videos are starting to appear there. So we have 4 servers, 4 clients, and you'll see the videos start to appear. In this particular case, the graph that I've shown, it will not actually show any video in here because they are not yet kind of connected to the seamless virtual cloud, right? So now here, what we are going to show, can you stop a little bit? So I'm just showing just portion of the the demo we have created. There are a lot of things there, but I'm just showing the highlights, right? So here, what we are showing in here, you can see that the admin has already created 2 portions of the seamless virtual cloud. So here, a CSP1 site, here CSP2 site. So this is California, New York, this is Texas, right? what we are going to do, remember I talked about the horizontal reachability control. So we have a concept called bridge, isolation bridge. What it does, it just basically use that API to actually bridge two different cloud service providers. So you'll see that just a node, two edge, and then a lot of things will happen underneath. What is happening underneath? Basically connecting using layer 3 MPLS VPN. Yeah, we can run it. So you see that it will connect these two isolation abstraction, which are now currently, as I said, mapped to a layer 3 MPLS VPN. This one maps to multi-S layer 3 MPLS VPN. So submit it. So the programming will happen in the network, and then you will see now all the videos. See that now everyone is connected to everyone, so you see all the videos there. So this is the last part to show that we can do all this thing on demand. So what this is doing now, it is actually deleting the New York site, right, on demand. Just one click, it's gone. And you'll see the video on the New York side has stopped, right? See, stopped. Now this one also stopped because that server was, taken out from the seamless virtual cloud before, right? So, so that's the idea in here is that first of all, you should be able to create cloud on top of cloud, right? We call it kind of cloud squared. Provided a very simple graph-based abstraction that gets mapped to programming the network using OpenStack and SDN. It could be any SDN. Right now, in this particular implementation, we have mapped to layer 3 MPLS VPN, including multi-S MPLS VPN, but you can also map the abstraction to IPsec, to VPLS, to any other network isolation technology you have there, it can be mapped. Okay? So, that's about it.
Thank you, Masum. Very interesting. Well, while you're thinking about your questions for the panel, and we have a microphone here, so raise your hand and we'll bring the questions. I wanted to start by asking any of the panelists who'd like to wade into the question, what standards do we need to be developed to enable this cloud networking, this SDN world that you're talking about? Who'd like to answer?
I'll start. I mean, there's been a lot of sort of what we call sort of API fatigue. So many vendors started out thinking that, if they expose their API, we'd get to this nirvana. And I think networking people are used to this notion that a Cisco router has to talk to another router, a Juniper router, an ALU router. So the interconnectivity, I think, is something that we tried to reuse, and I think that's something that we can agree on. Let's not reinvent how we exchange protocols to do that interconnectivity. Where the gaps are around, number one, system level abstraction, and I think Masum kind of referred to that. We need to be able to abstract the network in a way that the network can be consumed as a service by northbound applications. Because I talked a little bit about the convergence before, a Linux systems admin who's coming out of school today obviously is dependent on the network, but he's not going to be the triple CCIE who knows every esoteric CLI command. And that's where I think the networking industry has been, lagging a little bit in being able to lead this discussion around intercloud. The other piece is just around service enablement. There's been a lot of work around how we automate network services. I think there's a lot of good industry level work. There's a lot of discussion around that in forums like OpenStack and CloudStack, where an orchestration system needs to be able to present a networked service, whether it's DNS or DHCP or load balancing or caching or firewall or DDoS or any IPS, any of these services that we know well in the networking industry, but it needs to be done in a vendor-agnostic way. So we spent a lot of our time with cloud architects around that notion. We've been very focused around sort of the network service automation piece of it. The connectivity, I think we are very much invested there, and we also are using the baseline of RFC 4364 IP VPNs so that we can create essentially multi-tenant segmented user groups with clear network access controls. But on top of that, I think, is the services and applications. That's where I think a lot of the brain trust is moving.
Okay. Anyone else want to address that?
Yeah, I'll just add a little more. So clearly there would be many consumers of what we are developing as an industry, and we need to make sure that we enable a big ecosystem of developers so that the value can be propagated across different segments of users. And clearly for that we need to have a consistent, uniform, standardized interface. So that's one area where I think there is effort going on to standardize or enable applications to write applications to any controller that they may interface with. The other area is federation, and the federation is again at different levels. One is, as I mentioned, between overlay and underlay, or even between Intercloud, as Steve pointed out. So those are the two areas that I see that we need to work as a community to come up with something that's standard that can benefit everybody.
Okay. Let's take some questions from the audience, please.
Okay.
Tell us who you are and
sure. Yeah, I'm Sejun Sung from University of Missouri, Kansas City. Thanks for the good communication. In the discussion of this Intercloud federation, lots of challenges. I think how to federate is also important, but another thing is once we federate, right, I think the problem will be also federate too, right? So even we have like an apple tree from my neighbor, whether I can cut the tree in my yard or can get the apple from there. There are a lot of different rules and then complexity there. But the important thing is in this kind of cloud federation problem is we may not be able to see whether this problem is really rooted from where, who's the ownership of the problem. So my question is two things. Do we have any auditability or identification to those problem ownership? Another thing is, do we have those rules to consolidate those problems? I think we should also worry about those things because those things will be realistic, and then that may be the big block to federation in addition to the technology.
I think that's an excellent question. One thing that we learned in the development of the internet, and I think it's a lesson that we need to apply to the development of the cloud, is that we don't know everything that's going to be done with this asset that we're developing. In the early days of the networking, we didn't have the concept, for example, of a firewall. Everything had an IP address. The idea that you'd have a box where packets mysteriously went through and were processed, but didn't have endpoint IP addresses wasn't thought of. There'll be a lot of these challenges that come up. You've mentioned a couple of them. One of the things we're doing in the IEEE is there's a study group on cloud computing management that we're just starting up. HP is the chair of the study group, and among other things, he'll be looking at those challenges that you mentioned. Other panelists want to weigh in on that question?
I will, but I started last time. So.
Masum?
Yeah, so I mean, the federation definitely has multiple aspects to it, right? So, I mean, if you look at cloud, there are multiple layers there. I mean, layering is not going to go out. In fact, in the cloud, layering is very important, right? So, the cloud, so for example, you have this the cloud layer, right? underneath you have the network. So the when you are if you are writing cloud application, for example, the you may not want to actually expose everything from the network. So you have to actually abstract things out from the network, right? So you have the network abstraction layer, but it has to be kind of compliant with the cloud requirement. One of the major requirement is the on-demand, right? So I talked about the MPLS VPN there, right? So in a cloud environment, you should be able to actually CRUD or create, read, update, delete various aspects of MPLS VPN on demand, which is not easy to do these days unless we have the capability there, right? Now, IETF, I2RS, working group is kind of working in that space. Hopefully they will get in there, but the on-demand aspect is not there. So that's the networking part. Basically, you have to abstract there. Then you move up at the cloud layer. From there, you have to provide interface, which we call the tenant-facing interface. Again, another level of abstraction to the tenant, right? So if you are federating, now federating could be between multiple service provider. In the community cloud, it could be between multiple private clouds, right? Federation also can happen again, at these various layers, right? In the networking, you know, right? Juniper already talked about it. There's federation already happening, like BGP, MPL, multi-AS, MPLS, VPN. Similarly, at the cloud layer, we have to do that. Hopefully, Intercloud will get there, but that's a different layer, right?
Jennifer?
Yeah, I wanted to add, I think as we move from this notion of sort of centralized system administration to self-provisioning, because this is, a lot of the design summits were around this notion of user-based group policy. How do we automate? So, distributed control is one thing in terms of the network connectivity. But if I'm, let's say, Wikipedia, I want to be able to allow end users to edit that web page within certain bounds, and I, as the administrator, will set that policy, and from there, essentially, users are mapped into that user group. This is obviously in mobility. Guest access users have certain rights that native users do not. So if you think about mobility controllers and how those user group access policies have been set, it's a similar concept. One of the things from a Contrail controller perspective, we have a fairly flexible rules engine, and we've created this notion in a multi-tenant environment of role-based access control, and essentially those user group policies are embedded into the function of the controller, but each user group has the ability to set administrative controls and policies around what users can or cannot do.
So just wanted to add another perspective. So we've been talking at the cloud and virtual level, right? So when two cloud providers federate and their users possibly use resources from both the clouds, we need to enable the cloud providers to have a joint troubleshooting infrastructure as well, because at the end, it is the underlay that's carrying all the traffic and mixture of all the traffic. So how do you isolate problems is also going to be a big problem that we as an industry need to look at.
Excellent. I think we have time for one more question.
James, we'll give it to James.
So this question for Steve. It seems like
Talked about the number of standards being developed in the cloud computing space, because I used to have a slide which has about 40 organizations developing standards in the cloud computing space. It's certainly possible, and I won't speak specifically about OpenStack, for any organization that is interested in bringing forward work into the formal standards world to do that, and we in the IEEE have done this in the past numerous times, of taking work as a contribution and moving it forward to formal standardization. In fact, in P2302, there are contributions that are coming into P2302 from outside standards groups, and we would welcome any organization that had work that they thought would benefit from processing through the international standardization regime. I do think that there is an interesting difference, and I might mention that the kinds of standards that IEEE develops, for the most part, are open, consensus-based, voluntary standards. There are standards that are developed elsewhere in the world that are not voluntary-based standards. They become de jure standards and have legal strictures in front of them. And there are also different kinds of standards development mechanisms that have to do with who can participate, how that participation works into the process. And many organizations have different mechanisms. IEEE is different from IETF, is different from DMTF, is different from JTC1, is different from OpenStack. A lot of these organizations, many of these organizations have been in operation for many years. OpenStack is relatively new. And they all have their strengths and different values. And I think it's important to look at the evolution of standards and consider how standards can progress through other organizations. And that may be something that would happen to the OpenStack work, and we'd certainly be very, very interested in talking with them, should that be something that they were interested in. I think we're, yeah, absolutely. You have the microphone.
So I think
it's not on though.
I think
now it is.
There is a bit of a delay. So one of the recent trends, if you actually, especially addressing the networking vendors sitting on the table, there has been, we were talking about the overlays and the underlays, right, and the orchestration engines there. And as more and more vendors basically start dabbling in both the underlays, the physical topologies, as well as the overlay, right? I mean, HP does the SDN controllers and the switches. Cisco has Open Daylight switches. Juniper has Contrail and the switches as well. The reason why all these different models we are talking about have to be sort of carefully orchestrated, right? The orchestration of the orchestrators in some ways, is because there is an impedance mismatch between what the underlay is and what the overlay is. And what I wanted to basically ask each of the panelists to say a few things about what could be done in terms of reducing that impedance mismatch. It is, I mean, so some of the observations which are made were about, let's actually not rip everything apart, let's use what is already there. So assuming as things move forward, would the impedance automatically reduce, or are there actually technology research problems that you see that might be interesting for the rest of the research community to work on to reduce that impedance mismatch?
We'd like to address that. Jennifer?
Okay, I'll start. So one of the first things that Juniper did after the acquisition of Contrail was to converge the Contrail team and the team that was doing, management and automation of the physical underlay. So I think, like most of the panelists here, the physical network is not going away. However, it does make sense to try and simplify what is in the physical underlay and push a lot of the dynamic automation into a pure software layer. Now that could be, directly associated with the physical underlay as well. The more that it's software, it can be loosely coupled software components. But I think what we're trying to do is essentially establish a very robust and resilient physical underlay and push a lot of the dynamic automation into a software layer that essentially is loosely coupled from the physical underlay. And that way we can take advantage of the cost curve and the Moore's Law cloud computing economics and put into x86 environments what makes sense. Some things will need to be done in ASICs, but where we can, the control plane, the service plane, the management has already moved to an x86 model. In the forwarding plane and some of the high-speed security services, for instance, it may make sense to do that in premium hardware. But for the most part, I think we very much subscribe to make sure you're thinking at the system level, but from a management perspective, what the administrators need to be able to do is quickly correlate what's happening in the physical underlay and the virtual software overlay. And that's one of the first things that we've been working on, is essentially how do you do a trace route in the virtual software overlay and then correlate that diagnostic information with what you saw in the MX router or the the SRX firewall. That's something that we're working on very actively. And by the way, there's nothing about the standards were written from an overlay perspective. It also would be the same thing, whether it's an MX router from Juniper or a Cisco ASR 9K or a Trimetra router. All of those routers at the level of RFC 4364 support IPVPNs. What we're trying to do is eliminate the need for an extra gateway to bridge between the virtual software overlay and the physical underlay that already exists and is pervasive in MPLS VPNs.
Mo?
Yeah, so as I mentioned earlier, all the virtual traffic has to be eventually carried over the physical, right? So like Jennifer said, physical is, or the underlay is not going to go away. And we need to see how we move the intelligence away from the physical more to the virtual so that it's instantaneous, easy to create end-to-end solutions and so on. But at the same time, be aware of how the virtual maps to the physical and ensure that all the troubleshooting, or in some cases, if there are elephant flows, if they need certain special treatment and need to be redirected with the awareness of physical, on an exception basis, you may want to leverage the knowledge of the underlay to better service the requirements of the overlay network. So you have to have some awareness, and again, the awareness is with the cloud providers more than the end users. So we have to provide enough tools to be able to diagnose and better transition or map certain kind of flows to specific routes on the underlay.
Yeah, so I mean, I think the definition of overlay underlay is a little murky to me. If you're talking about underlay or UC, right? The underlay, it is being virtualized too. I mean, think about NFV, network function virtualization, right? At that layer, the lot of network functions are being virtualized, right? It's a big area there. Like, let's say your IPsec gateway is being virtualized. Cisco has this, the virtualized IPsec gateway called, or MPLS VPN gateway called CSR, right? So the virtualization is happening at all layers. So overlay is virtualized, underlay also is being virtualized. The other thing, as I've been pointing out, the layering is not going to go away. So the layering is will be there. So that's why I'm saying that overlay and underlay is a kind of murky, because the point is that if I think about the network layer, which is, let's say, layer 1 to layer 4, again, there is a kind of overlay and underlay there, right? So then, you have these cascading layers of overlay and underlay you have to deal with. But one of the main things that you have to consider in the cloud environment, cloud has a specific requirement, right? Which is, the main requirements are on demand, and you have to be the scalability there, right? So anything that has to happen in the cloud environment has to happen on demand. Now, we can talk about overlay, underlay, and anything. The on-demand aspect is not being considered much in many of the discussion, right? So again, I keep giving an example. Let's say that if I have to basically, program the MPLS VPN network, I have to do that actually on a on-demand basis. For example, in this particular, in our case, for example, we have to inject what is known in the MPLS VPN extended community route target. So I should be able to actually inject and withdraw extended community route target on demand. We cannot quite do that, right? So for that, it's better idea is to actually define a kind of overlay there, right? And then MPLS VPN layer itself remains an underlay, but the overlay layer becomes on demand, right? And then programmatically, basically, you program the underlying layer. So there, again, the thing here is that there are cascading layers there. There are cascading layers of underlying overlay there we have to consider.
Thank you, Masum. Well, I want to thank all of you for your interest and your good questions. I hope if you have further questions, you'll talk with us afterwards. I work in Silicon Valley. I'm GM of the Industry Standards Group at EMC in Santa Clara. I'd be glad to talk with any of you, although here I'm representing IEEE Cloud Computing Initiative. I want to thank Jennifer Lin, Amol Mahajani, and Masum Hasan. Please give them a round of applause. And thanks to Deep and the organizers for inviting us.
Thank you, Steve. We debated what to give to the panel for agreeing to do this, and we did a lot of thinking. And we decided what could be better than having a picture book about clouds. And it's an extraordinary cloud. So we have a book for each of you.
Thank you. Thank you very much.
So our closing ceremony will be actually very short, and it will start with the program committee, technical program committee chair, Punit Sharma, announcing the best paper award, and I have a couple of more announcements after that.
Thank you, Deep. So, best paper. Before I actually reveal the winner, we did actually go through extensive process of trying to see what the best paper was. Shortlisted 6 papers out of the initial 20 that we had accepted based on paper review ratings as well as the review discussions amongst the TPC. These 6 shortlisted papers were actually debated by 3-member selection committee at the conference on the basis of what the camera ready paper was, as well as the presentation. And the winner is the paper on virtual network embedding with co-location by Carlo First, Stefan Schmidt, and Anya Feldman. And I would actually like to give these certificates to the authors who are here. Before I hand over the mic to Deep, I do want to actually thank you all for the participation in the conference, because the exciting technical discussion wouldn't have been possible without all you guys being here. So, and hope you enjoyed the conference. We definitely did setting up the technical program for the conference.
Hello. For the conference, we awarded 3 student travel grants, and one of them actually had to leave early today, so we gave it to him. Let me see if the other 2 student travel grant awardees are here. So they get a cash award, which IEEE will send it to them to partially support their travel cost, and also get a certificate. So Dahe Kim, is he here? Okay. Who had to leave was Muhammad Said Sadiqi. He had to catch a flight. Oh, you are here. You already stole the certificate earlier from me. Maybe we won't give you the money then. All right. And the third student travel grant is Hasan Nikanfar. Is Hasan here? Okay, Hasan is not here. Okay. All right. So then I would like to thank all of you for attending the conference. I'd like to thank all my student volunteers helping out with many of the things here. And also, we did send an email about the survey about the conference. Please complete it within a week of this conference. And finally, I want to make, and then there will be next year's CloudNet. As you can see, the flyer will be in Luxembourg. Actually, the timing is slightly different. It will be in middle of October instead of middle of November. And so we encourage you to participate by being involved in a program committee, by submitting papers, and of course attending it. And then let's see, one more thing. Finally, I'd like to thank Punit Sharma, who is here for running the technical program, and I have a certificate for him as a token of appreciation. And with that, we close our conference. Have a good time and see you around in this same series of conference or somewhere else. Thanks, God.
Same time.
Yeah, please, if you are holding it, so we'll stage it. So we have done. No, it's okay. So take another one, this shake hands. Yeah. As if you're passing it on the other. Yeah. Hold it this way. But don't shake your hands. Very, very good. And I was glad you were still. I was worried that you won't be there. So I was very happy to see you.
Thank you very much, Bridget. Yeah. I will come and celebrate at 7.
Yes,
Thank you.